Let's find a power series centered at 1 for f of x equals the natural log of x and its interval of convergence. Okay, we have no idea how to do that directly, do we? Not yet. But we do have a result from the last example that could help us. So let's go back to the last example and look. In the last example, we have our power series looks like, where did I put it? This. No, this. Let me look at the right thing. What was that a power series for? 1 over x. So let's be clear here. This power series is 1 over x. What's the integral of 1 over x? ln, technically absolute value of x. But I don't think we're going to need to worry about the absolute values here because our radius of convergence is going to be limited. In fact, it's going to involve these endpoints. So it will just be natural log of x. So the idea is we could take the power series we just developed for 1 over x and integrate it. And that will give us a power series for natural log of x. Does that make sense? Which we would have no idea how to find otherwise. Okay, so let's do that. Let's take this guy. I'll just copy and paste. You guys will have to copy the old-fashioned way. So I'll say this. From the last example, if we hadn't already done the last example, we'd have to do all this work here, all the work from the last example here. But from the last example, we know this is true. So the idea is we're going to integrate it. So we know that the natural log of x from x equals 0 to 2, we know that the natural log of x is going to equal, let me put this before it, the integral of 1 over x dx is going to equal the natural log of x for x between 0 and 2. That's certainly true. So you don't need the absolute values there. And so what we're going to do to compute the natural log of x is we're going to take the integral of our power series. So the integral of the sum n equals 0 to infinity, negative 1 to the n, x minus 1 to the n power dx. And then we'll have it. We'll have our power series. We'll have to put in a plus c and figure out what c is, but we'll have it. So if we integrate that term by term, what do we get? So this guy, you can leave the summation notation out front and then just focus your eyes on the nth term formula. Remember, negative 1 to the n, it's just a constant. Don't worry about it. Worry about x minus 1, integrating x minus 1 to the n. And keep the constant there, though. So negative 1 to the n, it's going to stay there. Negative 1 to the n. X minus 1 to the what? N plus 1 over n plus 1. And then what do? We add in a c, right? So, but the thing is, we have the ability to find out what c is in this case because ln of x is a known function. If ln of x weren't a known function, we wouldn't be able to find c. But what do we know? We know ln of 1, right? We do know ln of 1, and we can use that fact to find c. So use the fact that ln of 1 equals 0 to find c. Again, if you're just integrating a kind of a generic power series and you don't know what function it represents, you can't do this. You just have to put in plus c and be satisfied with that. So why can I do it here? Okay, so remember, we're saying this is the natural log of x on the appropriate interval, right? This guy is the natural log of x on the appropriate interval. So if I go natural log of 1, then that means, everybody look up. If I'm taking the natural log of 1, I can plug, what am I plugging in for? X, 1 right there. What happens to every single term in this power series if I plug in 1 right there? Even the first term, every single term will go to 0. So if I plug in a 1 right there, every single term zeroes out, and I'll get 0 plus c. But I know the natural log of 1 is equal to 0, so I know c equals 0. So the actual sum without the constant, without the plus c, is correct in this case. Okay, so what do we have? We have, let's just write it down. The natural log of x is, on the appropriate interval, which we'll talk about in a second, is equal to the sum from n equals 0 to infinity, -1 to the n, x minus 1 to the n plus 1, divided by n plus 1. And that's going to be true, at least on this interval. From x equals, well, not x equals 0, but x between 0 and 2. Now, I'm not going to check 0. Everybody see why? ln of x is a known function. What's the ln of 0? Does it exist? No, it's undefined. So there's no reason, I mean, use your head. You don't need to check 0. But if ln were defined at 0, you'd want to check it to see if this series is convergent there. So we're checking, if I didn't make this clear, we're checking for convergence at endpoints now, because that can change when you integrate or differentiate a function's power series. The endpoints, the interval will be the same except possibly at the endpoints. So we do need to check 2, because this thing could be convergent at 2. So check endpoint x equals 2. So what does this series become when x equals 2? We get the sum, that stays the same. -1 to the n stays the same. Oh, I'm plugging in right here. So what do I get in parentheses right there when I plug in 2? 1 to the n plus 1, that's just 1, right? So I'm not even going to write that factor down. I get -1 to the n over n plus 1. What kind of series is that? Alternating, yeah. And you probably suspect it's going to converge, yeah. I'll leave that proof to you, but student, you should show this is a convergent alternating series. I don't know why I capitalized the A there, but I did. Okay, so then what's the appropriate domain for this power series representation of the natural log of x? In other words, what values are we allowed to plug in? Another way of saying that is, what is the interval of convergence for the power series? Domain, interval of convergence. In this case, since this power series is a representation of a function, I, the interval of convergence, is the same as the domain of that function. The domain is the set of all values you're allowed to plug into the function. So what's it going to be between?
0 and 2, 0 not included.
There you go. Just like that. Okay, so the full answer would be this.